Okay, so what I would like to do now is I would like to first discuss what happens if you have two wells and then extend to n wells, and that would lead us into the discussion of the band theory, which is the foundation of modern electronics. So what happens if you have two wells? So let me draw the potential energy landscape. So these are the two wells. Okay. I'm sorry, I cannot draw very well. It's very hard to draw on iPad because it's all slippery and things. So let me choose the coordinate system. So this is the potential energy. This is the x-axis, okay? And I would call this, this is U naught right here. This is U naught. And let's say this is L. And let's say that this distance is A, okay? So the centers of wells are distance A apart, away from the center. We have a symmetric situation. I define, actually, I think it's better if let me call this distance A right here. The distance between the wells, okay, between centers of wells, okay? Okay, and now I will ask you, what do you think the wave function would look like now? You are equipped to answer that question, at least qualitatively. You know how to answer that question qualitatively. Because you know that here, it's going to be sinusoidal. Let me use green for wave function. Wave function is sinusoidal. Here, it's growing exponential. Okay. Inside the second well, it's also sinusoidal. Here, it's decaying exponential. And in between the wells, it can be a sum of growing and decaying exponentials. Because remember, we eliminated the decaying exponential on the left because it has infinite area underneath it. And we eliminated the growing exponential on the right because it has infinite area underneath it, because you go from minus infinity to that position, and then from minus infinity to the left of the left well, that's infinite amount of space. So there will be infinite amount of area underneath the decaying exponential. And similarly, there will be infinite amount of area underneath the growing exponential to the right of the right well. But in between the two wells, you can have both growing and decaying exponential. So you can have a linear combination like this, or you can have a linear combination like this. In other words, they can have either the same sign or different signage. Okay, so growing plus and minus decaying exponential. So you know the structure. You already know the structure, right? Okay. So let's put it together. Let's draw the wave function. You know that the ground state wave function will have only one lobe, one piece of the sine waves. You know how inside the well, we have something like this, then something like this, then something like this. And it's true that these things don't have to go to zero at the edges, but there's still a piece of a single lobe of sine wave. Here's a piece of two lobes of the sine waves, and so on. And so we can draw the two possibilities. Here's possibility number one. What I'm going to do is I'm going to draw the axes for the wave function. And I want to notice while I'm at it, the potential energy is one animal, the wave function is a different animal. You really cannot put them on the same axis. It's like putting apples and oranges on the same axis. The only reason I do that is to superpose the horizontal extent of things. But I think that's actually causing the confusion to people. So instead, what I will do is I will, here, these are the wells, okay? So I think this is probably better. So here's possibility number one. You have a piece of a sine wave. And then you have something like this, you have this. And in between here, you have a sum of growing and decaying exponentials. And the net result is like this. So this is wave function number one. So this is one possibility for the lowest lying wave function, the wave function of the lowest energy. By the way, since we're at it, let me tell you some identities. This is called cosh. It's called hyperbolic cosine, and it looks, it's a function that looks kind of like this. It's not a parabola. These bits behave like exponential bits, and these bits also behave like exponential bits, and between it has this shape. Okay. And then there is another identity like this. This is called a cinch or hyperbolic sine. And it looks like this. It goes through a zero. So it's basically this is called hyperbolic sine right here. So it asymptotes to growing exponential here and decaying exponential minus the decaying exponential here. And it's a sum of those two. That's what it looks like. So this is x. Since this is a, by the way, appropriate moment. So what's another possibility? Well, the other possibility is to have the following situation inside the wells. So again, now this is the wave function, and this is the x-axis. Here are the wells. See, this is the reason sometimes I draw everything on top of the same graph, but I realize that students don't understand that U and psi have different units, they're different animals, okay? So the zero of the wave function has nothing to, the wave function does not have to converge to this thing right here, because this is, the red is the energy, the wave function is a different animal. So really, they should be drawn on the separate graph until students understand the subject. Okay, so what's another possibility? Well, the other possibility is to have a positive piece of a sinusoidal function, and it will be matched by a growing exponential here, and a negative piece of a sinusoidal function, and then it's matched by, a decaying exponential here. That's another possibility. And in between, you have this type of a combination of a growing and decaying exponential, right? So you would have something like this. You would have something like this, okay? So this is another possibility. So let me just summarize them. Psi 1 looks like this, and psi 2 looks kind of like this, okay? The probability density, well, I drew the real wave function, so the probability density is just the square of this, right? So this is P of x, probability density. The important thing to realize here is that it is not zero. You see, this thing does not go to zero. If you evaluate this thing at x equals 0, you get 1. You don't get a 0. Whereas the probability density here is strictly zero. So if an electron is described by psi1, there is a non-zero probability of finding an electron in between the wells. And by now, this should not be a shock to you because we already saw that it's possible to find a particle in the classically forbidden region, right? So if you have energy level that's like this red line, classically forbidden region is in between the wells is classically forbidden region, but you can find a particle here. I want to remind you that the wells are really a model. You can probably build a system out of capacitors that looks like a pair of wells, but it's really a model. So this is a model for example, two atoms. The model for two atoms. In an atom, what you have is you have a positive core, positive ion core, or just a proton. And then you have an electron, or I guess you have pairs of electrons in this case. And what does each electron feel? Well, first of all, each electron experiences a Coulombic force. We don't deal with forces, we deal with potential energies. And so the potential energy of each electron is a Coulombic potential energy. It looks like this. This is what two atoms actually are. So an electron, each electron, so I'm only drawing one electron, but each electron would feel this kind of a potential energy of interaction with these two ion cores. Each electron also feels repulsion from the other electron. For some really interesting reasons, we can get most of the answers, energies, wave functions, correctly without having to worry about electron-electron repulsion. It's called a non-interacting theory, where we ignore interaction between electrons. And therefore, when we look for wave functions, we will look for a single electron wave function. And each electron will be described by a single electron wave function. In practice, electrons do interact. And these kinds of single electron wave functions that we find, they're not completely correct, but they go a very long way to finding energy levels. And that's what we really care about when we put a lot of atoms together. We want to know what energies particles can occupy. So this is a more realistic potential energy landscape. And this is just a model. This is a model potential energy landscape. Okay? This is why we're doing it, but it goes an extremely long way because you already know how to solve this square well model. You already know the structure of the solution. You don't have to do any math to put together two candidates for the two lowest lying wave functions. This, on the other hand, requires a lot of math. But qualitatively, results would still be very similar. That is why we're working with models. Folks, models are a miracle. And particularly, I am very fond of a simple model. So for example, in my research, I make very heavy use of simplified models. Now, building a simple model is an art because it has to be sufficiently simple that you can solve, but it has to capture the essence. And so this thing right here captures the essence of what's going on. So the details of the two wave functions in the realistic case would be different, but qualitatively, the conclusions would be the same. Okay, I'm just telling you that as a fact. So let's go back to the model. So you have two candidate wave functions. the next candidate wave function would probably be something, so you take something like this, and then maybe something like this, and then the other one would be something like this, right? The next higher line, right? So psi 3, psi 4. And you can, when you look at it, you would say, oh, so it looks almost like constructing a wave function out of the sums and differences of an electron wave function in each individual well. That's really what we're doing. We're using, that's what we're doing. We're constructing the full wave function out of the building blocks, where each building block are the wave function for an individual well. This is, it would not be wrong to say that. Notice these are different wave functions. They have different electron density, right? So this one, the one on the top, this one has a non-zero electron density in the middle. This one has a 0 electron density. This wave function and this wave function, they have different curvatures. And so in general, they will have different energies. Unless the two wells are really far away. What does really far away means? Far in comparison to what? Well, far in comparison to the penetration depth of the wave function away from each well. Remember, inside it's a sinusoid. If I look at a single well, it's a sinusoidal, and then it decays over a certain characteristic region, 1 over kappa. If you go 2 kappas away, it's almost 0. And so 1 over kappa is called penetration depth. And so when the atoms, when A is much, much larger than 1 over kappa, when A is much, much larger than the penetration depth, the energy of psi 1 and psi 2 would be the same. But when you bring the wells close enough, or when you bring the atoms close enough, that individual wave functions begin to overlap, the energies would not be the same. The energy on psi 1 and psi 2 is generally not the same unless they're so far away that it's just individual wave functions that only differ by flipping a sign. Sign does not determine the energy. But when you bring the wells close enough and the wave functions begin to overlap, then in general, energy of psi 1 and energy of psi 2 would not be the same. If you want, we can chat more about this, and I can show you with Schrodinger's equation why you can, it's actually pretty easy to see why the energies of psi 1 and psi 2 are the same when the wave functions don't overlap. But in general, they're not the same wave functions. They have different electron densities, so they have different energy. So what happens energetically is the following. When wells or atoms are really far, you have basically just one single energy level. And when you start bringing them close together, the energy levels split. So this is E1 and this is E2. And what I'm graphing here is I'm graphing, this is A, and this is energy of these two lowest lying levels. Now, there isn't like a specific point where it clicks and it splits, okay? It just eventually, as A goes to infinity, they approach the same value. And that same value is the value of the ground state energy of each atom individual. So you have one atom in Chicago and the others in New York. They're not interacting atoms. And the energy levels of each atom is the same. But when you start bringing them together, then the two lowest lying wave functions, being psi 1 and psi 2, will generally have a different energy levels. And so that's what this splitting is. And so this crossover point is approximately like 1 over kappa or 2 over kappa or something like that. When A is less than 1 over kappa, when A is less than penetration depth, you have a serious overlap between the wave functions, and energy levels would generally not be the same because they're not the same wave functions. When they're far away, they're not the same wave functions, but they only differ by a sign, and it's almost like you have two individual separate atoms. So this is very interesting. In chemistry, you know what this is called. So in chemistry, this is called bonding state, and this is called anti-bonding. And this is bonding energy, and this is called anti-bonding. There's another way to see why this happens. Let's say I have two atoms. An electron in this atom sits in the ground state wave function, and an electron in this atom sits in the ground state wave function. I bring them together. Is it possible for each of the two electrons to sit in the ground state wave function? So in other words, is it possible, you start with ground state wave function, you bring them together. Is it possible that each electron is still described by the same ground state wave function? The answer is not possible. And the reason it's not possible is because of something called Pauli exclusion principle. Simplified version says that you cannot have a particle like an electron. Some particles you can, but things like electrons, protons, neutrons, they cannot be described by the same wave function when they're in the same region of space. And so therefore now, one electron has to be described by one wave function and another has to be described by another wave function. So this is what would happen when you bring them together. One electron would occupy this wave function, psi1, or we would call it occupy orbital psi1, and the other electron would occupy psi2. That's okay, that's allowed. And when they occupy different wave functions or different orbitals, they can exist in the same region of space. There's a caveat here that's related to spin. Technically, they can occupy the same wave function because there's another degree of freedom called spin, but let's ignore that. So, because of Pauli exclusion principle, while both electrons have energy E, the ground state energy, when they're far apart, when you bring them together, one would have to be at a different energy level than the other. And that's another way to see why there would be a splitting of energies. Because one would occupy a different wave function than the other, and in general, the two wave functions would have different energies. So this is a very interesting energy splitting phenomenon. When you bring two atoms and the atoms begin to interact. Now I will ask you, what happens if I bring three atoms? Now, if I bring three atoms. So this is two atoms. And now I bring three atoms together. It would not take too much imagination to realize that they split into three levels. So there will be three wave functions. What if I bring in 20 atoms? Why go to 4, right? Let's go to 20. And you get the picture. You get 20-fold, generally you get 20-fold splitting. So let me see if I can do this. So you would get a whole band. This is called a band of levels. So far I talked about the ground state. You see, this is the ground state of atoms far away. This is ground state. So it's the ground state that splits, right? So this all concerns the ground state, the state in which there's only in which there are no nodes inside the atom. But then we can talk about we can put other wave function, we could cook up with other wave functions that are based not on ground states but excited states. And so this is a ground state. So if I include not just ground state, but also is first excited state, so this splits into a band. This splits into a band. This splits into a band. And I must say, now I will just tell you that as a fact, that the ground states split less, the first excited state splits more. So you would get something like, maybe in practice, you would get something like this. This one splits even more. And why is that? The reason is that ground state is more tightly localized around the atom, and the excited states, they're more relaxed, they're more spread out. You saw that in our discussion. The penetration depth of higher states is larger. So they would split earlier and they would split more. So actually I should draw something like, they would begin splitting earlier and they would split more. Because they're less localized. And remember, what matters is the overlap of the wave functions. So it's something like this. In practice, if you have an atom with 20 electrons, some electrons occupy ground state energy, some first excited, some second excited. And it's the outer shell, we call them outer shell electrons that in the most excited states that contribute the most to this splitting. And so if you have Avogadro's number of atoms, if you build a crystal, you end up with having a band structure. So if you build a crystal, in practice, what happens is that the outer shell electrons, so you build a crystal out of each individual atoms. When you take the atoms far apart, each atom has an outer shell electron, an electron in the most excited state. When you bring the atoms together, those electrons that form the most excited, that came from the most excited state of each individual atom, they form this kind of a band. And so now, if you have n atoms with 20 electrons each, and each atom contains one electron in the most excited state. For example, sometimes it's more than one. Sometimes it's 2 electrons in the most excited state. But let's say each electron brings with it, each atom brings with it 1 electron in the most excited state. Well, what happens is now you build a crystal that has a band with n wave functions. Each of which has slightly different energy level, but the energy levels are lying very, very closely together. So really what I should be drawing is I should be drawing something like this, right? So you end up with a band of solutions, band of wave functions with very, very, very closely lying energy levels and E's. So this is a band of energies. It turns out that electrons in the top band is what contributes to conduction in some materials. If the top band is completely filled, if there are as many electrons as the number of levels in the top band. You get something called, if the top band is completely empty, you get something that's an insulator. And if the top band is half filled, you get a conductor. And moreover, the gap between this band and the top band controls the electronic properties of material. So in practice, what you have is, now this is just the energy axis, I'm not going to draw the distance, is you have these two bands. This is called the valence band, and this is called the conduction band. And this is called the band gap. This is discussed in modern physics too, but band gap controls electronic properties of materials. And the reason that this is important is that you can artificially modify band gaps, not by forcing the atoms closer or further apart together, but by introducing impurities. That process is called doping. And by introducing impurities, you can engineer the gap structure that you want. So all I'm going to say here is that whether a material is an insulator, a metal, a semi-metal, or a conductor, a semiconductor, it depends on what fraction of the bands are filled by electrons. If only the valence band is filled and the conduction band is empty, you get an insulator. If the conduction band is partly filled, in other words, if some electrons end up occupying the wave functions that correspond to the conduction band, you get a conductor. If the conduction band is completely filled, again, it's not a good conductor. If you have a valence band that's filled and conduction band, if you have a valence band that's filled and conduction band that's empty, but the band gap is small, then it's possible to excite electrons from the valence band into the conduction band fairly easily, and you get a semiconductor. I don't want to say much about the zoology of or classification of materials depending on the band structure. My goal here was to show to you where the band structure really arises from. You can trace it back, you can unroll the levels of difficulty, and you can understand the origin of the band structure from what you already know. You can use simple models to understand the origin of the band structure. So what I'm going to do, I'm going to pause. I'm going to show you some simulations for a little bit, okay? So here are the two wells. And I would like to, so here are the two wells, and here are the possible, so I'm showing you the wave function. I'm showing you just the real part of the wave function. And I paused the video because when I show you the real and imaginary part, the wave functions oscillate. It's the full wave function, the total wave function. So this is the big psi 2 or the big psi 1, right? Here's the big psi 1. It's a function of space and time. Its temporal dependence is just e to the minus e over h bar t. And so if I let the time run, it oscillates. I'm going to pause the time. So here's the real part. And right here, you cannot even see the two levels are almost the same because the atoms or the wells are really far apart. So here are the two wave functions that I was talking about. One you can build by having positive lobes in both wells, and the other by having negative lobes right here. So positive, negative. And here are the two wave functions here. Now you can see a tiny difference. You can already see the effect of the splitting. Here's the one with a positive sign, and here the one with a negative sign. So these are built out of the excited states that have a single node inside each well. Now I bring the wells together. So let me focus back on the ground state. I'm gonna bring the wells together until you start seeing splitting right here. You can start to see splitting. And so you see here's the ground state wave function, and here's the one that's built out of the individual wave functions with a minus sign. These ones are already pretty darn split. Okay, and you can see there's more electron density in between the atoms in this one than in this one. In fact, in this one there's a 0 electron density. So actually, let me plot the probability density. So here's the probability density in the bonding, and here's in the anti-bonding. So far, there's not much difference, but the difference is more pronounced here than here. So I bring them together. Now let me really bring them together. You can start seeing splitting, really splitting. So I don't need a magnifying glass. Here's the probability density or electron density in the bonding state and in the anti-bonding. There's more electrons in between the atoms. In this case, these are artificial atoms. There's more electron density in between the atoms in the bonding state than in the anti-bonding state. So right now you have bands made out of 2 levels. And before I go to many wells, let me show you with the 1D Coulomb potential, right? So you get basically the same idea. Pay attention to the bottom, just pay attention to the bottom right here. As I bring the atoms further apart, hardly any difference, but as I bring them together, the wave functions begin to overlap. And you can see that the bonding state has more electron density in between the atoms than the anti-bonding. This is more like realistic atom. Not completely realistic because it's a Coulombic potential in 1D. Realistic would be 3D. And the 3D situation is more rich. Anyway, so let's go back to square well. And I'm going to put not 2 wells, but I'm going to put n wells. So here's 10 wells. Okay, if they're far apart, let's see what I can do. I can do the following. I can make the wells narrow. I can make the wells narrow, and I can make them. Yeah, let's see. Let's see. What can I do? Let's do this. Okay. Yeah, let's do this. Here is the situation far apart. You can see all the ground states, they're almost the same energy. Not exactly, right? So with 2 wells, we saw that there is a solution with plus plus and a plus minus sign. With n wells, there will be n different solutions that arise out of the ground state energy. And the way you build them together is by a combination of a single well wave function with different phase factors. Okay, so it's not plus minus or plus plus, it's e to some phase, right? So it's a more complicated linear combination. That's what I'm trying to say. The most ground of which is all of them are like plus, 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 plus. The highest energy out of the combination that you get out of ground state wave functions is like plus minus, plus minus, plus minus, this kind of a thing. And so the lowest is plus, 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 the highest is plus, minus, plus, minus. And then you have everything in between. They're all kinds of combinations of phase relationships from one atom to the other. It's quite complicated, but qualitatively, it's still true that you get a band of different wave functions that each electron can occupy. And so if you bring n electrons, one will occupy this one, the next one will occupy this one, the next one will occupy this one, and so on. That's okay. Pauli exclusion principle does not prohibit that. Then you have a band inherited from the first excited state. Again, this is kind of like plus, 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 plus. This is plus, minus, but it's more complicated. Then you have all kinds of things in between, and they all have different energies. So this is the band that results from the first excited, and this is the band that results from the second excited. And you can see the higher the level is not, the higher the level is, the more spread out the band is. So the bottom is essentially like still kind of like one energy level. This one is still kind of like one energy level, but this is more like the band. And that's your band structure. That's the origin of the band structure. Now I have only 10 atoms here. If I have 1,000, it would look almost like a continuous band, right? It's very easy for an electron to jump from this level to this level just by thermal fluctuations. Temperature can kick electron around within the band, but not from one band to another. And so let's go to 1D Coulomb. I would have to adjust the parameters, but you can see that there are two bands here. I'm not sure if this is the equivalent of the valence band and this is the equivalent of the conduction band. It could be, I'm just not sure about that. Besides, this is a 1D periodic potential. It's not very realistic. The 3D is more realistic. But you can see that here you have two bands. And I think this would be the valence band. This would be the conduction band. If the number of electrons per atom, or the number of valence electrons, the outer shell electrons, is such that this is half filled, you get a good metal or a good conductor. If this is fully filled, you get an insulator. If this is empty and this is fully filled, you get an insulator. If the valence band and conduction band are close to each other, you get a semiconductor. Then it's not super hard to excite an electron from the valence band, in which electrons are immobile, into the conduction band, in which electrons are mobile. And you can dope the material with impurities that allow electrons, that act like stepping stones for electrons to jump from the valence band into the conduction band and conduct electricity. So you can design whatever electronic structure that you want, depending on what's the natural electronic structure, right? So you have a rich variety of materials with different band structures. And out of those materials, you have a rich variety of doping protocols or techniques that allow you to design the electronic structure of materials that you want. And that's basically where the semiconductor industry takes its origin. So that's what I wanted to say. That's the origin of the band structure. I think the big picture is, with the very limited information that you already have, one well, artificial things like square wells, you already have enough vocabulary, enough of stepping stones to understand more grown-up things like bands. And there is not a big step for you right now from where you are to understanding the band structure relevant to semiconductors. You can at least see where the band structure comes from. It all begins with very simple things that we're already discussing in class. So nominally, this class is not supposed to cover more than this, but I thought that you already have the vocabulary, so I might give you this optional lecture, optional discussion, to show you that there is actually not such a big gap between your current knowledge and more grown-up stuff. But if you really want to learn this stuff, well, first of all, you could take Modern Physics 2. That's where the band theory is discussed. And then more advanced classes would be solid-state physics, quantum mechanics, statistical physics. So those of you who are physics majors, you will be exposed to this information in more precise ways. But I thought this is already, you already know enough to have grown-up discussion. Okay, well, thank you for your attention.